Hello everybody, and welcome back to another geometry lesson. Today we're going to take a look at lesson 10.4, where we're going to learn about different angles and how to use them inside of circles. So, one thing I'd like to mention is, it is most useful for us to recall what a central angle is. If you recall, a central angle of a circle is the angle you get when you put an angle directly in the middle. So if you have a circle with the middle marked off, something like this one, if I could draw it all the way, there we go. A central angle is going to be the angle you could draw here and here. If this angle is 110 degrees, then the arc that it intersects is 110 degrees. But that's not always going to be what we're dealing with. In fact, what we're going to be talking about today is what happens if the angle was placed somewhere else on the circle instead of the middle. This is what we get when we make an inscribed angle. So to make an inscribed angle, instead of having an angle that has its vertex in the center, make an angle whose vertex is actually on the side of a circle. Something like this angle, A, B, C, would be an example of an inscribed angle. Now when we look at this angle, it looks like it is made up of two chords. That is what we would call an inscribed angle. So the definition is, an inscribed angle is an angle whose vertex is on a circle and whose sides are chords. So, if I make my angle here, let's say this angle is, I don't know, let's call it 30 degrees. This would be our inscribed angle. Nice. Now, when we look at the arc that is opposite to this angle, it looks like it opens up a little bit more than 30 degrees. First things first, when we make an inscribed angle, we call this arc the intercepted arc. Intercepted arc. The word inscribed means an angle that's inside the circle. Intercepted means crossed by an angle. So the intercepted arc is the arc that is crossed by the angle. The intercepted arc is just an arc that lies between two lines, chords, etc. So if you have an arc that's trapped between two lines, that is an intercepted arc. Now here's the interesting thing. Our inscribed angle is always going to be smaller than the intercepted arc. The intercepted arc is always going to be double the inscribed angle measure. So if you know your arc is 60, cut it in half, you get your inscribed angle. If you know your inscribed angle is 30, double it, and you've got your intercepted arc. You can go back and forth, either cutting it in half to get the angle, or doubling the angle to get the arc. The measure of an inscribed angle theorem says this. It says, the measure of an inscribed angle, the measure of an inscribed angle is 1/2 that of its intercepted arc. Perfect. Let's use this information to help us out with our first example for today. Our first example is going to be a challenge because it's going to be tough to identify certain angles and arcs, but I'm going to show you some ways we can really track them down. So we're asked for exercise 1 to find the indicated measures given the diagram on the right. The first thing we need to find is the measure of arc AC. Now remember that 2 letters means that you're trying to find a minor arc. But with AC, it's sort of hard to tell whether the top or the bottom will be a minor arc. My suggestion is, if you can't tell if something's going to be a major arc or a minor arc, meaning greater than or less than 180 degrees, just solve for the measure of the arc. If you found the major arc, just subtract 180 and you'll find the corresponding minor arc. So I'm going to make the arc AC go around the bottom, because I think that one looks to be the minor arc. Again, I could be wrong, but we'll find out in a moment. Now remember, this is the intercepted arc. So we need to find the angle that intercepts it. In other words, we're looking for an angle who touches point A and point C and is across from that arc. Remember, this arc has to be in between the sides of the angle. So it makes sense that such an angle would be this one right here, angle D. Angle D is the inscribed angle because it's an angle that touches the side and it has the intercepted arc in between it. Next up, we just need to find the measure of this arc. So, to find the measure of this arc, we remember the measure of an arc is double the measure of its inscribed angle. Well, here we only have that the inscribed angle is a right angle, 90 degrees. Well, recall that if the angle is 90 degrees, the arc is double that. So what's double of 90? 180. So the measure of AC is 180 degrees. It turns out 180 degrees makes it a semicircle, so it's not major or minor. So it would work either way. Let's find the measure of arc DB. Now, this one's going to be a bit trickier for us. Arc DB, the arc that stretches from D to B, is a bit of a wider arc. I'm going to color this arc in red. Remember, with 2 letters, we are looking for the minor arc, so the one that's smaller than halfway across the circle. That red arc is arc DB. So we need to find what angle inscribes this arc. And to do that, we look at what angle touches both of the endpoints. It turns out it's going to be this angle, angle C. Issue is, we don't really know what angle C is. But there's a couple of ways we can do that. One thing is, we have a quadrilateral here, right? We could find the measure of the angle inside. The measure of the angle inside is going to be 360 minus 90 minus 112.5 minus 90. It's going to give us 67.5. Another thing to do is we could find the remainder of the arcs around the circle, but that seems like it'll be a lot more work than is necessary. In this problem, we know that the arc BD is going to be double the angle. Since the angle is 67.5, all I have to do is double that to get 135 degrees. Last but not least, we're looking for the measure of angle DCB, but we just found the measure of angle DCB. We just said it was 67.5 degrees. But if you wanted to, you could also take the measure of the intercepted arc and cut it in half to get the angle again. Very nice. Now let's take a look at the next definition. For this next definition, I have drawn a little bit of a circle here, and I want to see what happens when we have two different inscribed angles on a circle. Let's see what happens when I draw just one of those inscribed angles first. So I'm going to make an inscribed angle. I'm going to make it in green that goes down here and over to here. I'm going to label these points A, B, C. So this is inscribed angle B. When we inscribe angle B, it makes an arc that goes from A to C. So there we have arc AC, the intercepted arc. But now I want to try something a bit interesting. What happens if I make another angle somewhere on this circle that also intercepts arc AC? In other words, what happens if I draw this red angle here? Well, let's say we give some measures to this problem, and it might help us figure things out a bit more. Say angle B is 40 degrees. We know that the intercepted arc is going to be double that. So the intercepted arc, AC, would be 80 degrees. But if we have an intercepted arc, the corresponding angle that intercepts that arc is half of the measure. So if this arc is 80, angle D is going to be half of 80, which is 40 again. Wait a second. When we have two angles that intercept the same arc, those two inscribed angles are the same measure. So this is what the inscribed angles of a circle theorem tells us. It says, if two inscribed angles intercept the same arc, then the angles are congruent. Very nice. With that definition, let's take a look at example 2. Exercise 2 gives us, essentially, a diagram with a couple of angles on it. We have angle E, and we know that angle E is 75 degrees. So I'm going to mark off that angle in red. And we are tasked with finding the measure of angle F. Hang on a minute. What do we notice about the red angle and the blue angle? Don't they intercept the same arc here, arc GH? If two angles intercept the same arc, those two angles are going to be congruent. So if angle E is 75 degrees, this blue angle, angle F, is 75 degrees. Since two inscribed angles intercept the same arc. Love it. Let's take a look back at our definitions to fill in the last couple before we do the last two problems. Now, we are going to talk about something called inscribed polygons. An inscribed polygon is any shape whose vertices are on the sides of a circle. So I'm going to draw a couple circles here that we can use to help us with this problem. I'm going to draw a circle right here, There we go. And I'm going to draw one down here as well. Both of these will help us a little bit with the next couple definitions. So, an inscribed polygon is a polygon whose vertices lie on a circle. Lie on a circle. When we make an inscribed polygon, the circle around it is called the circumscribed circle. It's the circle that contains the vertices. So, let's draw a couple of polygons in these circles. The first thing I want to draw, the first polygon I want to do, is a right triangle. Now, we got to be careful. In order to draw a right triangle, what's the most important part? Well, it's going to be the right angle of the triangle. So I'm going to start by putting a dot down here, and I'm just going to make a right angle, or as best I can with the tools I have here. So there's going to be the first line of my triangle. If I want to draw a right triangle, I want it to be exactly perpendicular with this line. So I think right here, whoops, let me try that again. This line looks to make a perfect corner with that side there, right? This is a right angle. Now watch what happens when I complete this triangle. If I wanted to complete this triangle, I'd have to connect these last 2 points with a chord. So I'm going to connect it up with this chord here. But do you notice anything special about that purple line? This purple line goes right through the middle of our circle. We know that this means it's a diameter. So we just made a diameter. Kind of cool, but maybe it's a coincidence. Let me see what happens if I draw another different right triangle on here. So I'm going to start off with a blue dot here, and this time I'm going to make my triangle sort of tilt this way. Again, I want to make a right angle with the blue line, so I'm going to line up my ruler as best I can and draw out, whoops, the right angle. All I need to do now is to finish the triangle is to connect up those 2 points, and wouldn't you know it, when we draw this one, it also goes straight through the middle. So no matter what, however we decide to draw our right triangle, it's always going to go through the middle. This is what the inscribed right triangle theorem tells us. It says, if a right triangle is inscribed in a circle, then the hypotenuse must be a diameter. If a right triangle is inscribed in a circle, then the hypotenuse must be a diameter. Would it work backwards? Let's say I drew another circle here on my paper. I'll draw the center of my circle and make the circle itself. And let's say I just started off by drawing a diameter. We know that a diameter has to cut through the center, so I'll just draw this here. And now I'll just try to make a random triangle with this diameter. let's say the point is right here. If I connect up the sides of this triangle, take a look and see what happens. We get yet another right triangle. So, no matter what, if one of the sides of your triangle is a diameter, it's a right triangle. Or if you know you have a right angle, you know the hypotenuse is going to be a diameter. Last, most certainly not least, in 10.4, we have the inscribed quadrilateral theorem. This theorem says, anytime you have a quadrilateral that is inscribed in a circle, something else special happens. So I'm going to draw sort of a goofy quadrilateral here. I'm going to draw it with sides like this, 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 and this. So I'm just connecting up 4 random points on my circle, and it's trying to see what happens when we do so. We end up with a quadrilateral. Okay, Mr. Strager, I don't really know what's important about that particular quadrilateral. Well, something happens when we take a look at the 2 opposite sides of a quadrilateral that is inscribed in a circle. The rule is, let's say we call this angle 1 and this one angle 2, this one angle 3 and this one angle 4. Angle 1 plus angle 2 is going to make 180. Those 2 angles that are opposites are supplementary. The same can be said of 3 and 4. The measure of angle 3 plus the measure of angle 4 equals 180. Whenever you have a quadrilateral in a circle, the opposite angles add up to 180. That's why this problem down here works so well. Try adding 112.5 plus 67.5, and you will get 180. So the inscribed quadrilateral theorem says a quadrilateral can be inscribed in a circle if and only if its opposite angles are supplementary. Perfect. Let's take a look at exercise 3, and then we'll do exercise 4. Exercise 3 has us finding the value of each variable. And if we look at exercise 3a, we don't have much to go off of. When we look at this example, all we see is an inscribed triangle. But what's special about this inscribed triangle? Well, line segment AB goes through the middle, so that must be a diameter. If line segment AB is a diameter, then according to the inscribed right triangles theorem, this big triangle has to be a right triangle. Well, what angle is always across from the hypotenuse in a right triangle? The right angle. 2x is a right angle. In other words, 2x equals 90 degrees. So then, that's how we can find that x equals 45. Let's take a look at part B. For part B, we have a quadrilateral that is inscribed in a circle. So what's the rule about that? The rule of an inscribed quadrilateral is opposite angles, such as D and F, are supplementary. Remember, 2 angles are opposite if they are across from each other in the quadrilateral. So we know that Z plus 80 equals 180, for instance. That means Z is 100. z is 100. Similarly, we can find y by saying that y and 120 are supplementary. Y plus 120 equals 180. So then, y equals 60 degrees. Very nice. Let's take a look at C. Now, C is going to be a bit trickier, but I think it's important that you give this one a shot on your own. I will give you a little bit of a hint here. You will have to use inscribed angles alongside with your theorems about inscribed quadrilaterals. Think of this more like problem or example 1 than example 3. Pause the video, see what you can figure out, and just note there are multiple ways of doing this. How'd you do? Let's take a look and see what we can do. So, we know that an inscribed angle measure is going to be 1/2 of their corresponding arcs. So if we wanted to find more angles in this quadrilateral, we can just pick an angle, find out what arc it intercepts, and cut that arc in half. For instance, let's take a look at angle JKL. If we look at what arc this angle intercepts, it's this one, arc JML. All we need to do is figure out what JML is, cut it in half, and we'll have angle K. Well, since JM is 54 and ML is 130, this entire arc is 184 degrees. So what's the measure of angle K? Angle K is going to be half of that, which is 92 degrees. Now we can use this angle to solve for 4B, because opposite angles in a quadrilateral, an inscribed quadrilateral, are congruent. Sorry, not congruent, supplementary. Sorry about that. 4B and 92 add up to make 180. So 4B plus 92 makes 180. When we subtract 92 from both sides, we get 4B equals 88. And when we divide by 4, we get that B should be 22 degrees. We can do the same exact thing for angle J. Angle J here, that I've marked in green, intercepts this big arc KLM. KLM is made up of 110 degrees plus 130 degrees. That's 240 degrees. So this big arc is 240. That means the inscribed angle is half of that, 120 degrees. So again, we can say 3A plus 120 equals 180. Subtract 120 to get 3A equals 60, and A equals 20. Again, just know, when you have an inscribed angle, its intercepted arc is double its measure. We've got one last problem to do in this section, and this one's a bit of a doozy. Now, it is so important that we experiment with this problem. If you're watching this video after class, just know that experimenting and actually trying this out, trying different things, seeing what works, is going to be the best path to victory for this problem. Let's talk about it a little bit. Your camera has a 90-degree field of vision, and you want to photograph the front of a statue. So here is the front of our statue that we're trying to photograph. We happen to stand in like the perfect location. where the front of the statue is all that the camera can see. In other words, these dotted lines you see are the camera's view. We can't see anything outside of that view. That's what we want. We want to figure out where we can move our camera to still see just the red line here. And we want to see what locations are possible. This is a bit of a tricky one. Let me give you an example of what wouldn't work, and then we can see what would. Let's say, for a moment, I recreate this diagram. Not the best recreation, but it's what I could do with the time I had. We basically got a video camera pointed here at this red line. What wouldn't work is if I moved the video camera back. If I move the video camera straight back, we're still keeping the 90-degree field of view. So that means I would just redraw my angle here. My angle would go out this way, and to make 90 degrees, it would go down this way. And already we have a huge problem. This camera is capturing more than just the statue. We don't want it to capture these areas at all. Whoops, make it a little bigger. So that's no good. We can't move further back. What happens if I move the camera closer? Well, we run into a similar problem. If I move the camera too close, we no longer see the entire statue. All we get is a glimpse of this. Still a right angle for both of these, but we're not viewing what we need to view. We need our view to stop here and here. So this is also no good. Whoops, sorry, this middle one is fine. What if we move our video camera up or down? Same issue. We would be capturing part of the statue, not the entire statue. So what can we do? I'll give you one hint. I want you to pause the video and see if you can find a way to find different spots we can stand to still see the full statue. I'll be giving hints in just a little bit. Hopefully you took the time to pause the video and give this a shot. Again, trying this out is going to be the best way to understand it. Now, if we want to make all the spots that our camera could be, the question is, how do we make that happen? Well, there is a theorem that allows us to keep this angle the same while still moving the position around. This looks very similar to the inscribed angles of a circle theorem. This theorem says if two inscribed angles intercept the same arc, then those angle measures will stay the same. So if I had a 90-degree angle intercepting an arc, I could move that 90-degree angle around and it would still be 90 degrees. This also is something that's sort of said in the right triangle theorem. See, if we have a right triangle that's in a circle, then the hypotenuse must be a diameter. Wait a second. What if we used this as the diameter of a circle? Again, if you just wanted a hint, pause the video here, but if not, I'll give you the next hint in just a moment. So what if the red line was a diameter? Let's see what happens. If the red line's a diameter, then this center of that side is the center of a circle. Let's see how to draw this circle. We center our compass. We look for how far out we want this circle to go, sort of testing out what I see, and I see that this point right here circumscribes our triangle perfectly. It's the circle that has our red line as a diameter. Okay, so what, Mr. Strager? Well, what's the measure of the arc that this angle intercepts? It would be this big red arc here. And because this is a diameter, we know that this arc's measure has to be 180. This is a semicircle. That means any angle that intercepts this arc, these two endpoints, A and B, will have to be 90 degrees. Now here's where I give the problem away, folks. Let's try drawing some examples of angles that intercept this arc. Well, what if I drew an angle that went from A to this side, then to B? Well, according to our inscribed right triangle theorem, if your hypotenuse is a diameter, then it has to be a right triangle. But more importantly, according to our inscribed angles of a circle theorem, if two inscribed angles intercept the same arc, like we're doing here, those two angles are congruent. So they're both right angles. What if I put my camera somewhere on the other side? I'll put it maybe really close to this angle. Well, once again, all we have to do is just draw the angle that still intercepts that diameter. And we still get a right angle. What if I set my camera to be really, really close to the edge right here? Once again, we just connect it up to the same endpoints that we have been, and wouldn't you know it, it's still a right angle. So, what's the answer? The answer to this problem is, you can put your camera anywhere along this circle that has the statue's edge as a diameter, and you will still get exactly the same angle measure. You'll still see the entire front of the statue. This arc AB, is where you can put your camera. That concludes 10.4 for us, everybody. Thank you so much for listening, and have a fantastic rest of your day.